Okay, so I said in the previous video that this function t here, that we just showed it's a linear transformation, but I specifically said that it's referred to as a stretch. And what it does is it stretches vectors by a factor of 2. Let's take a look at why that is the case. Okay, so what I'm going to do is I'm going to draw a couple of vectors in R2. So where's my black? Here it is. So let's start with these two vectors. Here's a point, the point 1, 2, and here is the point 2, 1. Now I'm going to draw each of these with a different color arrow so that we can actually match them up to different vectors that I'm going to draw on the other graph. So here's just two examples of vectors that you might plug in to the function t. So this vector here would literally be the vector 1, 2 if you wrote it in coordinates, right? Because its terminal point is the point 1, 2 and its initial point is the origin. So the blue vector is really, the coordinates of its terminal point are exactly the same as the coordinates of the vector that I've drawn in blue. And same with the green vector that I've drawn here. Its terminal point has coordinates 2, 1, but if you were to express this green vector as a coordinate vector, it would have coordinates 2 and 1. And that follows from the fact that its initial point is drawn at the origin here. So let's take a look at what the function t would do to these vectors. So here's the idea. I've drawn a vector in blue on the left-hand graph. T does something to that vector. If you plug this vector into the function t, it's going to change it. And it's going to change it according to this formula. So what is the output vector going to be? Well, if you actually work out t of 1, 2, plug in 1 for x1 and 2 for x2, you're going to get 2 times 1 for the first coordinate and 2 times 2 for the second coordinate. That's going to give you the point 2 and 4. So let's sketch the point 2, 4 here. It's going to look something like this, be about there. So that's the point 2, 4. And really, if you plug this vector here into the point t, into the function t, you're going to get this vector back as output, just based on the formula. And if you plug this vector here in, the vector 2, 1, if you plug that into the function t, well, again, it's going to, remember what t does, it just doubles both of the coordinates, so you'd end up with the vector 4, 2. So if I draw its terminal point over here and draw it starting at the origin, we're going to get this vector. So this is the point 4, 2, and this green vector, if you wrote it out in coordinates, you'd get the coordinate vector 4, 2 as well. So this picture, you can see what t does. It doubles the length of the vectors. It stretches them by a factor of 2. So that's what that means. So notice the strategy I used to turn this into a picture. I didn't graph the function t officially here. All I did is I just picked a couple of vectors. I could have chosen different vectors, but these ones illustrate the point quite nicely. I picked a couple of vectors over here, and then I drew them on this graph, and then I drew the corresponding output vectors on this graph that you would get if you plugged both of these vectors into t. And that's a way that you can get an idea of what a linear transformation is actually doing, or a vector function in general. Okay, so that's the end of that example. Let's look at another one. So here's an example of a function that goes from R2 to R2. So it takes as input a vector with 2 coordinates, and it gives you back as output a vector with 2 coordinates. And it does so based on this rule. So let's take a look. And you notice I've written this one out in column form. Right, so it tells you what t does to a vector with 2 coordinates. Right, the 2 coordinates are x1 and x2. Well, it gives you back this vector, which looks like it has the same values for its coordinates, but they've traded places. Right, so that's what t does. It swaps the coordinates of whatever vector you plug into it. And so notice that the input vector has 2 coordinates, that matches up with this. And the output vector also has 2 coordinates, that matches up with this. Now both of the examples we've seen so far, both the input vector and output vector have had the same number of coordinates, but that doesn't need to be the case. Okay, and we will see examples where that's not the case, but for now, this one just happens to have that property. Okay, well let's start with the 2 conditions that we need to verify. The first thing we need to do is show that t of x plus y is equal to t of x plus t of y for any 2 vectors x and y in R2. So let's start with 2 vectors x and y. So I'm going to say let x be a vector in R2, and I'm going to write out its coordinates just like I did in the previous example, but I'm going to stick with the same notation as the way the function was defined. So I'm going to use column vectors to express my vector x and y. So we can write the vector y as y1, y2, and those two vectors are the most general vectors in R2 that you could ever possibly write down. Okay, so let's work out t of x plus y and try to show that it's equal to t of x plus t of y, because that's what we're asked to do. We're asked to show that t is a linear transformation, so we have to try to show that. So let's start with t of x plus y. So what is x plus y? Let's just write it down. X plus y. Well, we're just going to add the two first coordinates to get the first coordinate of x plus y. I won't do this every time because after you do it a few times, you start to see the pattern here. But then if I add the two second coordinates, I'll get x2 plus y2. This is considered side work, so I'm not going to include this in my main thread. But this is what's going to allow me to go from this step to the next one I write down. I'm just going to change this to t of x1 plus y1, x2 plus y2. Okay, so now we've added the vectors x and y, and this notation says the brackets say to add those two vectors first. So now we're going to apply t to the result. And well, in case you ever forget, just look up at the definition of t to see what it does. What does it do? It swaps the two coordinates. So what that's going to be is x2 plus y2 as the first coordinate, because that was the second coordinate of the input vector. And then now for the second coordinate of the output vector, I'm going to take the first coordinate of the input vector. So that'll be x1 plus y1. So that is what you get if you plug x plus y into t. But we're not done yet, because if I just pull up the definition of a linear transformation as a reminder, remember what we're trying to get. We started with t of x plus y. We want to get t of x plus t of y. We want to get this as our result. Well, this is going to have to be broken up into the sum of something. One vector plus another vector, and then we're going to have to cross our fingers and hope that those two vectors are t of x and t of y. So let's follow the same approach we did last time. It's probably a good idea to break this up into two vectors, the sum of two vectors, one of which has all the x stuff, if I'm allowed to speak informally, and the other one that has all the y stuff. In other words, has all the y components. So let's do that. So the first vector is going to be completely independent of y2 and y1. It's just going to have x2 as its first coordinate and x1 as its second coordinate. And now that's not true currently. As I've left it now, if I stopped now, this is not true. But I can add the vectors y2, y1. Okay, so that is the decomposition here. This breaks up into the sum of these two vectors. But now, let's looking at this one in particular will give you the hint as to how to proceed now. Because if you look at the vector x2, x1, that looks an awful lot like this one, x2, x1, right? It's the same thing. So what is this? It's t of x1, x2. So this is actually t of x1, x2. Let's write that, t of x1, x2. And then what's this one going to be? Well, it's y2, y1. This is exactly what I would get if I plugged this vector into the function t, because t would swap the coordinates. So if I plugged this vector into t, the y2 and the y1 would trade places, and I would get this. So this is actually t of y1, y2. And now we're done, because this is x, right? So this is just t of x. And then this one is t of y. Caught me writing a bit small there because I wanted to squeeze that into one line. I should have maybe backed this up a little bit to the left. But that means we started with t of x plus y, and through it linking all these equal signs, we ended up with t of x plus t of y. And we didn't assume anything special about x and y, except that they had two coordinates each, so that they were in R2. So that means this statement has now been proven for all x and y in R2. So let me just do the same bracket thing just to say that is the argument to verify condition 1 in the definition of linear transformation. So now we just need to verify the second condition. So we'll start off in the exact same way that we started the previous example. We're just going to start with a vector x in R2. So again, I'm going to write a general vector x with 2 coordinates as a column vector. But I'm not going to pick a vector y this time, because for the second statement, all that is involved, or all that's mentioned for relative to this equation has to hold for all vectors x and Rn and for all scalars k. And in our case, n is equal to 2. So we've already got our vector x in R2, but we need to now choose an arbitrary scalar k. So that's why we're going to say, and k be an arbitrary scalar. So if I just say let x be in R2 and I say nothing else, then that means it's an arbitrary vector in R2, and we're not assuming anything special about it. And same with the scalar k. We're not assuming anything special about it other than the fact that it's a real number. So now we're going to work out t of kx, and we're going to see if that gives us k times t of x, right? We're going to try to verify this equation. So we're going to start with the left-hand side. We're going to try to manipulate it until it's equal to the right-hand side, using only the rules, right? We can't break any rules of vectors. But as long as we follow the rules and we end up getting k times t of x, then we're done. So let's work out what kx is. So got some space over here. Remember, kx, that's just a scalar product of the vector x by the scalar k. So it's just going to have the effect of multiplying both of those coordinates by k. So we're going to get kx1 and kx2. So that is our kx. So this next step is just going to look like t of kx1, kx2. So all we did is change notation really there. Nothing major happened. We didn't really do any work. But now we're going to apply the function t to this vector. So again, if you've forgotten, just double check what t does. It swaps the coordinates of the input vectors, right? T of x1, x2 just gives you x2, x1. So it swaps the coordinates. So that's what it's going to do down here. It's going to swap the coordinates. So the first coordinate is going to become kx2. And the second coordinate is going to become kx1. Okay, so that is what we get. And remember what we're trying to do. What's our goal here? We're trying to end up with k times something. So the fact that both of our coordinates have a common factor of k, that's a pretty good indication that we probably should pull that k out. Right, so we're going to get k times x2, x1, the vector. And then actually this is good because this vector x2, x1, remember what this is? That's actually t of x1, x2. So this is actually k times t of x1, x2. But x1, x2, that's just the vector x. So we can write this as k times t of x. And that completes it, because now we have t of kx is equal to k times t of x. And that works for any two-dimensional vector x and for any scalar k in the reals. So that finishes the second condition, and we can say, therefore, t is a linear transformation. So that, let's put a box around it since it's our conclusion. But that completes that example. So what is this function doing? This is a very specific type of function as well. So what did it do? Here's the hint is in what it did. How do you say what t did in ordinary language without having to refer to x1 and x2? Just say it swapped the coordinates, or it flipped the coordinates. Right? So this is an example of a flip or a reflection. That word is used a lot as well. So I'll call it a flip. So And actually, why don't we just put both words in here? Just mention or reflection, because both words are used often. And really, why is it called a reflection? Well, here's the picture. I'm not going to draw this one from scratch just because I wanted to pre-render it, so I made sure I didn't mess it up in the video, because it's sometimes if I don't draw it perfectly to scale, it doesn't work out too well. So, but this next sentence kind of explains it, right? T reflects vectors in R2 about the identity line y equals x. So you see this diagonal line that's hyphenated? That's the identity line y equals x, right? It's just a line goes through the origin, has a slope of 1 over 1. Or alternatively, you can think of it, it just goes up at a 45-degree angle or a pi over 4 angle. And the effect that this function has is it essentially just flips vectors across it. Let's look at the yellow one, for example. I've color-coded them so they match up. So let's look at the yellow vector here. It's got a first coordinate of 2 and a second coordinate of 1. So if you plug that vector into t, it's going to swap the coordinates, and you're going to get the vector 1, 2. And what that ends up doing is it swaps it across the identity line. It has, if you actually check, you can plot it by hand yourself to check, but that's what it does. It just flips it across that identity line. So that's what happened there. For the purple one, here we got 2, negative 2. So it's got an x coordinate of 2 and a y coordinate of negative 2. That's what brings us down here. If you plug it into t, it's going to swap the coordinates, and you're going to get this one. You're going to get negative 2, 2. So you have an x coordinate of negative 2 and a y coordinate of positive 2, that puts you here. So again, you can see that that's exactly what t did. It flipped this one around the identity line. And same with the blue one. Right? You can check that the blue one has coordinates negative 1, negative 3 down here. If you plug it into t, it's going to swap the order, and you're going to get negative 3 on the x-axis and negative 1 on the y-axis, which puts you over here. And so the picture tells the whole story. Right? It really does flip those vectors across that identity line. But again, notice I used the same strategy again. I didn't graph it completely because you can't. But you can pick a few vectors, plot them in the Cartesian plane, and then plot their images, which is what these vectors are called, right? These 3 vectors are actually referred to as the images of these 3 vectors under the function t. That's not terminology that you're responsible for, but if you're interested, you will hear those words used if you work with this stuff in other courses. But that's, yeah, I think that about summarizes it up.